Now we're going to start with the Rankine's earth pressure theory. So basically, we have started already with the retaining wall concept, retaining wall, types of the retaining wall that we have seen. After that, we have seen the most important topic is earth pressure or pressure at rest. After that, we have seen active earth pressure, passive earth pressure, numericals on a earth pressure at a rest, numericals on active earth pressure that you have seen. Now, the next part, the most important part is will deals with the different earth pressure theories. There are scientists who have given their own theory in order to calculate the earth pressure. So, very first thing is that we will start with the fundamental first author. Let's start with the Rankines. Rankine is in a year 1857 developed his theory of lateral earth pressure when the backfill consists of dry cohesionless soil. The theory was later extended by Russell in 1910 and Bale in 1950 to be applicable to cohesive soil. So we'll start with the Rankine's theory. This is just introduction. Now we're going to see the now we're going to see the next part, that is nothing but the its assumptions for this theory. Now Now we will going to see the assumptions which has been given by the Rankine's theory. The very first thing is that the soil mass is isotropic, semi-infinite, and it has been the soil mass is isotropic, semi-infinite, homogeneous, dry, and cohesionless. The ground surface is a plane which may be horizontal or inclined. The face of the wall in a contact with the backfill is vertical and smooth. This amounts to ignoring the presence of the wall. After that, the next is nothing but the wall yields about a base sufficiently for the active pressure conditions to develop. If it is the passive case, then that is under consideration. The wall is taken to be pushed sufficiently towards the fill for the passive resistance to be fully mobilized. Then the fifth assumption is the rupture surface is a planar surface which is obtained by considering the plastic equilibrium of the soil. So thus it has been seen that by neglecting the wall friction as also cohesion of the backfill, the geotechnical engineer on the safe side in the computation of the both active and passive resistance. Then next we will for element A to reach the failure state, the lateral effective stress must be less than the vertical effective stress. So if the shear stress induced in a soil is less than the peak or critical shear strength, the soil has reserved the shear strength, and we can characterize this reserved shear strength by factor of safety. Then for fixed condition in dilating soil, the factor of safety is tau p upon tau, where the ratio of lateral principal effective stress to the vertical principal effective stress at the limiting stress state is given by the equation. So equation is sigma 3 dash by sigma 1 dash, which is equals to 1 minus sine phi dash upon 1 plus sine phi dash. That is equals to tan square 45 minus phi dash by 2 equals to Ka, where Ka is the active earth pressure coefficient, active lateral earth pressure coefficient. After that, the next is for the same for the passive earth pressure Kp, which is equals to 1 plus sine phi dash 1 minus sine phi dash. So which is equals to tan square 45 plus phi dash by 2, which is equals to 1 by Ka. So Kp and K are always converse to each other. Okay. So substantially more movement is required to mobilize the full passive earth pressure than the full active earth pressure. So lateral earth pressure coefficients developed so far are valid only for a smooth vertical wall supporting a homogeneous soil mass with a horizontal surface. The lateral earth pressure coefficients must be applied only to the principal effective stresses. So this is what all about the information for the active and passive air pressure coefficient by using the Rankine analysis. So next is different cases. First case is effect of submergence. So when the backfill is fully saturated or submerged, the lateral pressure will be due to two components. The first component is lateral air pressure due to submerged unit weight of the backfill soil, and second is lateral pressure due to pore water. So in a first diagram, which is related with the submerged backfill, you can see that it has been due to the unit weight of the backfill soil. So it can be calculated as Ka gamma dash H, gamma WH, which can be calculated. Secondly, like next is wall with the submerged backfill and water on the other side. So it can be calculated as Ka gamma dash H. It is due to the pore water pressure. So, depending upon the same condition, now we'll going to calculate one the for a numerical. We're going to proceed for the numerical. Compute the intensities of active and passive air pressure at a depth of 8 meters in a dry cohesionless sand with an angle of internal friction of 30 degree and unit weight of 18 kilonewton per meter cube. What will be the intensities of active and passive air pressure if the water table rises to the ground level? Take saturated unit weight of the sand as 23 kilonewton per meter cube. So very first thing is that this numerical is having the two conditions. So it is has been divided into two sections, part A and part B. We'll focus first initially on part A part. Start with the first. What they give? They are given a earth pressure at a depth of 8 meters. So means depth is given as 8 meters and angle of interfriction is given as 30 degree. Unit weight is given as 18 kilonewton per meter cube gamma. So this is what the first we calculate the intensity of active earth pressure, where first we'll consider the dry soil. In an initial condition, formula of active air pressure coefficient Ka, which is equals to 1 minus sin phi 1 plus sin phi, where angle is given as 30 degree. So 1 minus sin 30 upon 1 plus sin 30. Sin 30 is given as 1 minus 1 by 2, and below that 1 plus 1 by 2. So we get the ratio as 1 by 3, and Ka is calculated as 1 by 3. So whereas Kp, coefficient of passive air pressure, is inverse of the Ka. So it has been 3. So you can easily calculate the formula 1 plus sin phi upon 1 minus sin pi, which is equals to 1 by K, which is equals to 3. So after that, we're going to calculate the intensity in active condition. So Pa, which is equals to Ka gamma H, which is equals to 1 by 3 into 18 into 8. The formula will be Ka gamma H. K is the coefficient, gamma is the unit weight, H is the height. So 1 by 3 into 18 into 8 will get the answer as 48 kilonewton per meter square. Next is nothing but the intensity of passive air pressure. Pp equals to Kp gamma H, 3 into 18 into 8, where Kp is the coefficient of passive air pressure, gamma is the 18 unit weight, and H is the height. So 3 into 18 into 8 will get the answer as 432 kilonewton per meter square. This is for the passive air pressure condition. So this is half part of the numerical. Remaining, they said what will be the intensity of active and passive air pressure if the water table rises to the ground level. So if it is water reaches to the ground level, it means that there is a submerged condition. So submerged backfill condition, we can use the formula gamma dash. Gamma dash is equals to gamma sat minus gamma w. So gamma sat means saturated, which has been given values in numerical as 22 kilonewton per meter cube. So 22 minus gamma w. Unit weight of water in MK system is 9.81. So gamma dash equals to 12.19 kilonewton per meter cube. After that, the intensity in active or pressure condition formula will be Pa equals to Ka gamma dash H plus gamma W into H. K is 1 by 3, gamma dash is 12.19 into height given as 8, plus gamma W is 9.81 into height is 8. So you will get the answer of Pa is equal to 111 kilonewton per meter square. So after that, for the intensity of passive air pressure, Pp equals to Kp gamma dash H plus gamma W into H, where Kp is the coefficient in passive air condition, gamma dash is unit weight, and in a saturated condition, H is the height, gamma again plus gamma W equals to unit weight of water in MAS system and H is the height. So Kp equals to 3 into 12.19 into 8 plus gamma W is 9.1 into 8. So we get the answer as 371 kN per meter square. So this is what the submerged backfill conditions answer, where you will get the answer as PA is equals to 111 kN per meter square for submerged backfill condition, and intensity of passive air pressure is calculated as 371 kN per meter square. And for the dry soil, PA is 48, and for the uh, same dry soil, coefficient of passive condition PP equals to 432 kN per meter square. So this is all the answers for the numerical. Thank you. We'll stop here.